Just making
Sure. Welcome everyone after the break.
Here, do you have to
it's like,
assist or not?
sure. So welcome everyone after the break. It's a great pleasure for me to introduce our next speaker. So that's a perfect coincidence because, you know, after lunch we're full, but now we have something exciting. So definitely we'll be waking up. So it's a great pleasure to pass the microphone to Chayes from Berkeley here, who is the main organizer of this event. Thank you.
Yes, I'm a delinquent main organizer of this event. So anyway, thank you for being here on, Friday afternoon of Memorial Day weekend. Some of you are going to know this. Some of you are going to see me give a lot of these slides. Some of you won't have seen me give these. So anyway, let me get started. So I'm going to very quickly review a couple of things that Christian talked about in his first three lectures: dense graph convergence and convergence for sparse graphs of a bounded degree. But what I really am going to concentrate on is sparse graphs of unbounded degree. So, things like power law graphs and other graphs that don't have a bound on the number of nearest neighbors, but are sparse. So we'll talk about convergence for those graphs. Then we'll talk about having a function, a graphon, corresponding to those graphs, such that if we can use it to generate realization samples of that kind of graph. Then I'll talk a little bit about learning how we estimate those kinds of graphs. So if I had something that I was measuring, how would I estimate what the corresponding graphon is? And we'll also talk about that for to do that in a privacy preserving way for smaller class of graphs. And then I'll give an application of this, okay? And stop me with any questions that you have along the way. I'm not gonna take you through proofs like Christian did, although I will try to help you understand where some of this stuff is coming from. Okay, so I know that Christian had this picture. I always like to start out. I mean, I assume that most of you here know graphs and adjacency matrices and that kind of thing. But okay, so we have a graph like the half graph over there, and I can take all the vertices of the graph, put it on two sides of my adjacency matrix, and if I is connected to J, I'm going to color it in black. And if it's not, I'm going to leave it white. And so there's the adjacency matrix of the half graph. And then I'm going to, heuristically take a limit. Okay, so what, just how would that look as things got finer and finer with larger and larger graphs of that form? Similarly, for the random graph, let's say the P equals 1/2 or the Schrödinger graph, I'm going to get, kind of a grayscale limit. And then, of course, there's a question about what about permutation of the vertices? Okay, these two graphs, I can permute the vertices of one graph to get the other graph. Those weird limits don't look the same, actually. They looks like they're going to look very different. And the fact that for exchangeable graphs, they're invariant under permutations like this. In the limiting image that you get, you have an even larger invariance. The invariance is invariance under measure preserving bijections, maps that are one-to-one and onto. Okay, but that's just a reflection of the permutation invariants that you're really comfortable with for a finite graph, for a finite exchangeable graph. And so with Christian and Laci Lovas back in 2010, actually most of our work, a lot of it is way before it was published because we take forever to get our papers done, as some people have tried to work with us. No. But this graphon that corresponds to the graph is unique up to measure preserving bijections. In my CARP lecture, I'm going to talk about graph vexes, and they are the corresponding thing that we have to mod out by to get a unique one is much, much larger. And interestingly, we did that with Laci Lovas Jr. many, many years later as a birthday present to Laci Lovas Sr. on a big birthday. And it was over 100 pages. So it was really ugly in some sense, but also really satisfying. And that was Laci Lovas's Sr.'s present. Okay. So, so Christian also told you about dense graph convergence. So the one that you really want to get your hands on because you can prove things with it is metric convergence. So we came up with something called the cut metric that harkens back to what Fries and Conan did in 1999. They looked at a given graph and they said, what is the max cut through that given graph? So just imagine I didn't have a W1 and a W2, I just had a W in there. And I asked, and T were equal to S complement, what is the largest cut I could take through that graph? Okay. So, you know, which edges would I be cutting? Okay. And that gave me some kind of a measure for that graph. So then what we did was we said, let us take the graphons, these limiting objects that correspond to those two graphs. Okay, if they don't, you know, so we assume that they're on the same space now. And I want to maximize the cut distance between them. But again, I must take the inf over all measure preserving bijections because it can look different depending on what measure preserving bijection I use. So I use the one which gives me the inf of all of those. And I say that that's the distance. So that's your very concrete analytical object that you use to prove things about all these other ones. Okay, this is all for dense graphs. So we came up with more, and in fact, one that I'm sorry I'm not mentioning with David Gamarnik, but maybe Christian mentioned it, I don't know, but one slide where it showed up. Okay, although I do have your name on one of my next slides. Okay, but we came up with what we called left or local convergence. So why did we call it left? We called it left because we thought of, Christian might have told you this, but you know, we thought of a big graph G homomorphisms into a little graph H. So I take my big graph and I mean, I could map it into something really small, like H could be an edge, okay? Oh, I'm sorry. Sorry, okay. So I should H into G, H into G. And anyway, let me just.
No, this is no right. No, this is not because it should be.
Oh my God, Christian. Exactly. Why don't you say it? I don't want to say it because he's my husband. Oh my God. So what we're doing is let me take my big graph G and map it into an edge. Okay. let me take my big graph G and map it into a triangle. Let me take my big graph G and map it into a 4-cycle or a Peterson graph or any finite graph you can think of, okay? And I could, I mean, it's like Moses transformations and stuff, but it's the same thing as looking at what is the frequency of edges in this big graph G? What is the frequency of triangles, of 4-cycles, of Peterson graphs? Okay. And now I have a whole sequence of graphs. And I ask, let me look as this sequence of graphs gets bigger, let me look at the density of all those finite graphs. And I ask that all those densities converge. That seems like a pretty local thing because, you're looking at at these tiny graphs, right? At these tiny things, and you're asking that all of them converge. And then Christian also talked about sampling convergence. Okay, so what I'm going to do now is I'm just going to go in and I'm going to sample K points randomly out of my graph. I'm going to do this on G1, on G2, on G3, and I'm going to look for the probability that H is an induced subgraph there, that the edge is an induced subgraph of these points, or triangle or whatever is the induced subgraph. Okay, and I'm going to ask that all of those converge. Okay, and actually, I think first place this appeared for dense graphs was Diaconis and Janssen, I think. The other ones here all came from, okay, whenever you see a B, and you will always see it in a set of names, it's Christian Borg's. When you see a C, it'll be me. When you see 2 C's, it'll be me and Henry Cohen. I think, well, the L will either be, most of the time here, it'll be big Lovaas, might be younger Lovaas, okay? S is Chayes, Vera Chayes, who I think of as the grand dame of discrete mathematics. She's amazing. And Kati Vestergambi, who is also amazing, and actually happens to be married to Lotzi and the mother of Lotzi Jr. Okay, so we did a whole series of papers with them. And so, but this thing actually, I think I saw first in Diaconis and Janssen. Statistical physics, since Christian and I come from that world, for us, it was a very natural thing to say, I am given this graph, and on it, I am going to compute, for example, a ground state energy. So what I'm going to do is I have a certain model, and this model says, there's a certain weight of, so let's say that, that I have 2 colors, up and down. Okay. We don't normally think of up and down as colors, but they could be. And what is the weight of an up being next to a down? What is the weight of an up being next to an up, or a down being next to a down? Okay, for these 2 colors. So now the sigma is just, configurations of every spin up or down, or it could be configurations if I have 20 colors of all these possible things. And I have these J's fixed, and for dense graphs, I divide through by the volume squared of the graph. And I can calculate a ground state energy given this model on this graph. And I can calculate that same energy on graph G2 and graph G3 and graph GI, and, and I ask that those converge. Those are actually not, they're pretty closely related in a lot of ways to multi-way cuts that you might do more in computer science, where you ask about cuts through the graph and what are the cost of these large cuts through the graph, and you look at the sequence of those, and so those things will converge on this sequence. And so it turns out that for dense graph sequences, and let me just, yeah.
Is there a way to think of the right convergence as some kind of approximate convergence of homomorphisms from the graph?
Exactly, exactly. Okay. Actually, that was precisely what we were doing. That's why we thought of it as right and left. That's precisely what we're doing. We're taking, we're taking some graph here, which actually kind of represents a coloring. Okay. And we're asking, what's the homomorphism of that coloring? A set of rules of who gets connected to who and with what weight. Okay, so I can have, red, yellow, blue, green. Okay, and I have a graph that represents, oh, if blue is connected to green, it has this weight, and if blue is connected to yellow or to red, it has those weights, and so on. So Ford choose 2 possible weights, and I'm taking that small graph and I'm mapping it into, and taking the big graph and I'm mapping it into these colorings. And that's kind of what this guy is doing. Okay, so it's precisely the way to think about it.
So it's even more technical. You might say the homomorphism is not a minimum, but there are 2 to the n configurations. And in this dense set,
Yes,
it is sort of, so in the end, that is all which will survive.
okay, so it is precisely that. Okay.
That's what Sparse graphs say.
So it turns out that metric convergence is equivalent to these apparently local and apparently very global things. Okay, and it's all really nice. And of course, dense graphs are graphs where the number of edges scales like n squared. Okay, you have a positive fraction of all possible edges. So you have basically, a positive fraction of positive edges in the non-zero possibilities in the complete graph, okay, on those endpoints. Okay, so now, oops, let's do that. Good. So now sparse graphs of bounded degree. That's a very, very different situation. Okay, so we actually looked at that with Lotzi and with Jeff Kahn, and then later in some of our stuff on something called large deviations convergence with David, which is really, really cool, but I don't have time to go into it here. We also looked at kind of at when you might see this kind of thing. Now, Christian talked to you about Benjamini-Schramm convergence, which long predated these things. So what Benjamini-Schramm convergence is that I choose a random vertex. So you're going to need this in your talks. Oh, you talked yesterday. Okay.
Here's the last talk. You are our crowning jewel of the
Crowning jewel. It's crowning, it's not crowning. But I am a crowning jewel. It's our anniversary. And so, on our 29th anniversary, I am a crowning jewel. Okay, so Benjamini-Schramm convergence, I'm going to choose a random vertex and I'm going to look at graphs rooted at that random vertex. So I might have a big graph and I look at graphs that are rooted at that random vertex. And I ask, and that's a very, very local notion, okay? And so that makes sense for graphs of bounded degree. I have no more than 29 neighbors in this entire graph, okay? So subgraph convergence turns out, so convergence of edges, triangles, blah, 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 turns out to be the same as that. And then convergence of free energies is a strictly stronger notion. It's what I would call the low temperature phase of that model with the colors, okay? And convergence that we're not learning about with David, large deviations convergence is strictly stronger all the time, Okay. So, these are much more fragile. Okay. I think of them really as much more brittle in a way than graphs of unbounded degree. Okay. So let's think of unbounded degree graphs. So there's a very simple one. I take the Erdős-Rényi random graph. So I have n vertices and each pair, yeah.
Clarifying terminology. You put equivalence between local convergence of Vinyash-Schramm. Is that just a definition or?
No, that's a theorem. That's a theorem. That's what we proved using cluster expansions with Jeff Kahn and
This
lots
is
of.
differential.
Oh.
The left convergence is subgraph. It's convergence.
Oh,
So you
okay,
ask,
that's the equivalent.
how
to
often do
Vinyash.
I see a triangle? You divide by n,
Yeah.
and this is by some inclusion, exclusion, and so on.
Cluster expansion.
No cluster.
Well, yeah,
You can
including
infer
the
it
same,
from-
the
you can
same
make,
expansion you do for a cluster expansion.
That's what was it.
Right, it's kind of Mobius of the inclusion exclusion. Okay, so I'm gonna say, and we all know, I hope that the random graph means at density P means that, the probability that any given pair of the n-choose two possible pairs is connected to each other with density P. And so what if P what if P is going to n as n is going to 0 as n is going to infinity. So, we often talk about the 1/n, random graph. So that will, then have, something like n squared over n, about n connections in it. But that could also be some other power. It need not be 1/n. Okay. Anything which goes to 0. So it could be, for example, log star, 1/log star n. It could go to 0 really, really slowly. And that would still be unbounded degree random graph. Okay, then we have stochastic block models. Okay, so the regular stochastic block model has k colors, and we have something which specifies that color, I is connected to color j with density beta ij, which is the same as beta ji, because it's an undirected graph. So reds and blues, reds and reds, whatever. And I'm going to put a p in front of that so that I can scale it. So what I have here is so I'm also specifying here the amount of red, the amount of blue, the amount of green, the amount of yellow, and that should add up to 1, the density of red, green, blue, and yellow. And I'm going to connect any pair with that probability. And I'm going to say that the p that I'm scaling everything by is going to is going to 0 as n goes to infinity. Okay, so then I can also generate a graph which has unbounded degree. Okay, I can scale it like 1/n, and then I get a graph that has of order n edges, but I can scale it in different ways going to 0. Okay. Then I could also do a fixed, these are simpler than the general case, a fixed degree sequence. So they're kind of getting harder as we go down this easier thing. So I have D1 up through Dn, okay? And what I'm going to do, so every point is coming in with its D, and I'm going to connect I and J. So I has degree 3 and J has degree 34, and I'm going to connect them with a probability that looks like 3 times 34 over the sum of all the Ds, okay? And if I scale this in some way, for example, if I say that DI looks like some fixed n to the alpha times n over I to the beta, then what happens is this gives me the probability that D is bigger than some K times n to the alpha, and it turns into a power law in K with beta is positive here, okay? So I can get a power law out of a fixed degree sequence if I have degrees that are of this form, okay? And so the question is, in general, develop a theory of sparse graph convergence, which includes these examples, you know, in particular allowing for power laws, but much more general examples too, okay? Very general examples, okay? So what's the problem with this? If we try to just blindly go and do what we did before for dense graphs, you know, edge density is, you know, the number of edges over the number of vertices squared, okay? And this goes to 0, okay? So the cut norm of this is bounded above by the 1 norm, which is the density. So this is going to go to 0. So everything works, but it works really trivially. Okay, all my limiting Graphons are 0. It's not wrong. It's just not interesting in any way. Okay, so you know, what have I mean, this is at least, you know, this is similar to the first thing we thought of doing. So, you know, what I want to do is I want to, let's say I want to normalize it, right? I want to normalize it so that the probability that these, K points that I choose is some fixed graph H. How would I think I should normalize that? Well, I should normalize it by 1 over the density to the number of edges, okay? And that you would think would help you, okay? And the only problem with that is that it's just way too brittle, okay? So, so if I had like P, okay, so if I had P goes like n to the minus 2/3, okay? Then let's think about that. Let me look at an edge, okay? There are n possible. So I'm going to look at an edge and an edge. So this vertex is here with, there are n possibilities for this vertex. There are n minus 1, let's call that n possibilities for that vertex, okay? And then the probability of this is P goes like n to the minus 2/3, so that's n squared times n to the minus 2/3. So it has n to the 4/3 edges, okay? Now, how many triangles does it have? Well, the triangles that it has are, okay, so I have n minus 1, n minus 2, that's n times, what did we say? N to the minus 2/3 cubed, okay? And so what happens is that I get only n triangles, okay? And so what I could do is I can remove all the triangles without removing, you know, with removing essentially none of the edges, little o of 1 of the edges. And so anything like this is not going to work, okay? It's just too brittle to do that. Okay, so what we did instead was 2 things, and I'll give you, and henceforth when I talk about sparse graphs, I'm always going to be talking about sparse graphs of unbounded degree, okay? I don't want to have to say unbounded degree every time, but I'm not talking about a bounded sparse graph. Okay, so one idea is instead of dividing here by v squared, okay, n squared, as I did for dense graphs. I divide through by the number of by the number of edges in the graph. At least I'll get something which is not zero then. And another thing is that I'm going to modify my left sampling convergence as follows. Instead of sampling k points, I'm going to let k scale. I'm going to say I'm going to sample Poisson t over square root of rho, many vertices from V. Okay, so I'm, you know, and rho is going to 0. Okay, and so I'm sampling more and more and more to compensate for the fact that otherwise it would be disappearing. And so the expected number of edges that I sample is k squared times rho over 2. And this gives an expected number of edges, which is uniform. So I'm compensating for that. And then I'm going to remove all isolated vertices and return the induced subgraph. And we call this rescaled sampling convergence. Now, these two turn out to be equivalent to something else that I'm now going to tell you about, okay? Which looks more like a metric, and metrics are good because we can prove things when we have a metric. So Olbosch and Reardon did this for W's in L infinity, so bounded W's, and then with Henry Cohen and Yufei Zhao, these got published much later than when we did them. We did this in a more general sense. So we said, what I'm going to do for my graphon is the graphon would be going to 0, okay? And so what I want to do instead is I want to divide through by 1 over that 0 density, okay? And so what I'm doing, so just think about our unit square here. And what I had before for a dense graph was kind of nice finite things there. And when I divide through by something going to 0, okay, these are going to get very big. Okay, so these heights are going to get very big. And then I'm going to define a rescaled metric, which is the difference between this rescale thing where I've divided through by this density that's going to 0 and my limiting W. So in particular, my limiting W is going to be unbounded. Okay, it's going to be on the unit square, but it's going to be unbounded. Okay, so that's a different thing. We were always seeing bounded W's in the dense case. Okay, and it turns out what you have to do is you have to prevent mass from leaking out to infinity. And so we came up with a regularity condition, which we called uniform regularity, in which we basically said that the probability that W is bigger than something as we get bigger and bigger and bigger is controllable, okay? So that mass doesn't actually leak away. We first did this in general using like an LP metric, and then we realized, oh, if you have an LP for all P, you actually get this uniform regularity. So, okay, so we said if mass is not running up to infinity here, then we're in good shape. And that turns out to be the same thing as taking the ground state energy and instead of dividing through by n squared, divide through by the number of edges, which coincided with n squared in the case of a dense graph, but not in the case of a sparse graph. And using these kind of new metrics with the rescaled graphons, we were able to prove things about that.
Jennifer, I have one silly question. It's an odd plus as the image of the potential image of the W. Can't you do something more so that it's just a compact interval which is not just a 0, 1. You are renormalizing it.
Not just, so the W
Yeah.
can sit on, it need not sit on a compact interval, but there's no, but it's sitting on, what are you saying, Christian?
So the limit is not compact, you can't complete it.
Oh, that's what she's asking. You're asking about a
Cannot be
completion.
that,
No, it is not compact. Okay, it's not compact. And that is why, I mean, otherwise you would just get a easy subsequential limits and you'd be like in great shape. Okay,
So that's
but all the
more or
work,
less what Polar essentially are.
yes, that's what Bela and Oliver did. And so theirs then had to be bounded. It had to be L infinity. And in this case, you don't get, in our case, you don't get subsequential limits.
So where Bella and Oliver, they normalize it by L infinity law.
No, but they are able to get it, they are able to compactify it if W turns out to be L infinity. They're able to get subsequential limits with no further restrictions because the mass is not leaking out.
Yeah.
Besides that condition, so you take this picture she has there.
Right.
Okay.
Rescaling.
And so just like it is, it goes to infinity. And then, and now your graph becomes finite. You get sort of higher towers in an empty Manhattan. There's a lot of empty space.
Yeah.
And now they put a condition that if you integrate over any finite region, so integral stays bounded.
Which means no mass.
So it's sort of weakly bounded. If you want in sort of some weird notion, so it's bounded if it stays integrate over a small region.
Small regions where the
Which turns out to be
kind of a
No,
point
so you
masses of
choose,
it.
so what is the condition? The condition is, so you fix some constancy, and then you take for any epsilon,
Yeah.
you can sort of choose, if you put groups where you don't have less than epsilon n vertices per group,
Yeah.
then the average graphon is bounded by
so it turns out.
all epsilon, for all C's exist.
So they're only doing it for bounded graphons, it turns out, okay? And we said, no, let us not, what did they call that? No, some kind of spot,
No dense spots.
no dense spots, okay? But of course, most of the ones we care about have these dense spots. So then to get the subsequential limits, because we didn't have the compactness by something like that, we had to do a lot more work, and we showed finally that you could do that LP for all P, and therefore uniform. If they were uniformly regular, if the probability that these graphons that are greater than whatever does not run off too quickly, okay, then you're fine. Okay, and that is how we got it, but it allows W being L1, L2, L27, uniformly regular. Okay. Okay. Now, think about doing something totally different. Okay, how do I make sense of this? The other thing that I could do is I could, instead of dividing through by W, I could change my metric, okay? And so what I'm doing is I'm stretching. So I'm no longer sitting it on the unit square. I'm stretching the underlying metric by square root of this W, which, by the way, remember, this is going to 0, okay? So I'm stretching it by that, okay? And so what you land up having, so we call this now the rescaled W, okay? So what we're doing is we're playing with the underlying metric, okay? And remember, this is, so now I get more and more and more and more and more points, right? Because I'm not, right? And that turns out to be equivalent in many, many cases, and I will, and if we modify that a tiny bit, in all cases, to the sampling, where you sample with a Poisson that makes you go further and further and further out. according to square root of rho. Okay, so this is equivalent to a modified version of left convergence under suitable regularity conditions. And maybe I'll define it later in this lecture. Maybe I'll define it in my CARP lecture. I don't remember. Okay, and the stretch graphon can be generated via a projective process on graphs. So this is me, Christian, Henry Cohn, and Victor Veitch. And it turns out to correspond to something that Victor and Dan Roy had done a few years earlier, defining something called a GraphX. Okay, but we can do that just, so I'll tell you there's this distinction between GraphXs and Graphons that I won't talk about now, but I'll talk about in the CARP lecture. Okay. But the nice thing about this, let me just say, well, you'll see it here, actually. So without extra technical conditions, mass can disappear, up to infinity, and so we don't get subsequential convergence for arbitrary sequences, except if, so that we have to apply this condition. So as I said, we developed these notions of regularity, uniformly regular tails or uniform upper regularity. Can we get a sequence which converges in both senses, the rescaled one and the stretched one? And what sparsity can we achieve? And the answer is, and this is with Nina Holden and Henry Cohn, if both of those converge, then it turns out that G is actually dense. Okay, so those are really different kinds of situations. Okay, and if either of those but not both converge, then if either of those converge, then it has divergent average degrees. Okay, so the advantages of the first, that scaling, you can get sparse power law graphs. It's equivalent to right convergence or multi-way cuts under this assumption of uniform upper regularity. And the advantages of stretching, it gives convergence with very long power law tails. The notion of left convergence can be generalized to sparse graphs, which he did with Henry Cohn and Victor Veitch. And under the assumption of uniform tail regularity, which I didn't really go through with you, it's equivalent to stretch metric convergence. And then we can also, and that I'll really do in the CARP lecture, extend the notion of graphons to something even bigger, which is the completion of the space of graphons. Then we get compactness and subsequential convergence without further conditions. Yeah.
Random graphs, the Vn is selected so that the average degree grows, is that right?
Yeah. Mm-hmm. Mm-hmm.
So it's slightly above this very sparse and fixed degree.
Yes, absolutely. But it could grow, very slowly. Yeah.
Technically, the fixed degree graph have unbounded degree because the largest degree is growing, but that's not the regime.
I'm talking, I'm unbounded. I'm sorry. Did I not say unbounded average degree out there?
It's
It's okay, I think you said average, unbounded average degree.
Divergent average degree.
Yeah.
Okay.
But Jennifer, so because we heard a lot of talks from economic networks, and it seems that they always assume this either average degree is log n, so that the graph is connected or network is connected or strongly connected. So indeed, this new theory.
You need this. You
economic
need this
networks are not that
technically
dense,
to be,
right?
yes.
But
Yes.
this, right? That's
Yes. So that's, the moment we conceived of Graphons, we wanted this because in applications, you always want this, okay? Any, Facebook, anything like that, they may actually prohibit you from having more than a certain number of connections, but in the real world, in social interactions, there's no bound, right?
but not that dense, right?
What? But they're not dense,
right?
exactly. But, think of, how many people unfortunately wanted to connect to Donald Trump on Twitter? I mean, okay. That's what it is. Okay. Okay. So we just done this part. I have a lot to do for you. I have this part and this part. So now what I'm thinking is, okay, so we're actually, you could put them in a sigma finite measure space. Yeah. And you could have a symmetric measurable function, actually. So now what I'm going to do is I'm going to take graphons of that form, and I'm going to use the function to generate graphs, to generate representative graphs. Okay, so the traditional approach to non-parametric graph modeling is to use the stochastic block model, which we've discussed before, right? I mean, I'm not saying P times beta here, I'm just saying P alpha beta. So I'm going to have, K colors, and I'm going to connect them according to this symmetric matrix of probabilities for red, green, blue, yellow. Okay, and then if you try to estimate this for diverging average degrees, estimating these P's, well, how does one typically do that in practice? They first determine what the group labels are. They first determine, what the densities of red, blue, yellow, green are. They use some kind of clustering, some kind of belief propagation. I mean, that's not rigorous. They were just using that, right? And then average the adjacency matrix over all edges whose endpoints have colors, red and blue, whatever, and they get the model. But, what happens if the model you're measuring is not a block model? Nothing comes out of those estimations to tell you, oh, you made the wrong assumption about the form of it. Okay, so it's not stable under misspecifications. So that's not what we want. An alternative non-parametric approach is inhomogeneous random graphs, which actually, without proofs goes back to 2002, and then others have worked on it. And instead of a matrix indexed by communities, the way I think of this is a function based on features. So given a feature space with a probability distribution pi, so what do I mean by that? Okay, let's say my features are my gender, my height, my age, my weight, my final degree, the field of my final degree among some 100 possible fields, and all these other things about me. Okay, I mean, just so many other things about me. And so what I want to do is I want to generate people points with this set of attributes. Okay, probably not going to be generating many with heights above 6'8". Okay, so my distribution is going to, the probability of that's going to be pretty small if I'm trying to, if I'm trying to generate people. And they're probably not going to be as many degrees in physics as there are in computer science and all kinds of things like that. So I have some probability distribution. So that's generating. So I'm going to choose these IID according to pi. Okay, so these are points in omega. So omega is my feature space. Certainly need not be one-dimensional. Okay, it typically is not one-dimensional, and it can include continuous things, and it can include discrete things, and whatever. And then I'm going to connect 2 points with, and I'm going to scale by the density appropriately, with the probability that if I have this height, this weight, this gender, this whatever, probability that I connect with Christian is whatever it is. Well, we both did physics and whatever. Okay. And then I'm going to have to be scaling it appropriately by a density, which is going to 0 because on Facebook or something, the density is, right? So then I'm going to call the resulting random graph an inhomogeneous random graph at target density rho n and denote it by this. So, let's just say you went to Facebook, you're a new employee, and they handed you the W and the rho n of Facebook, okay? And now you can start generating these random graphs, right? Okay, so that's one way of doing it, okay? The problem is if I think of a sequence of graphs here, they're not projective when I go adding up, yeah.
From the Christian's lecture, whenever we heard about Graphon, it was measurable, and the image space of Graphon was, of course, 0, 1. Now we extend it to the R+. So still, it's just symmetric and measurable. That's it.
It's
right.
measurable.
That's it, right? But I
because my measure space is, it need not be 0, 1.
Yeah.
Okay, and in the next example,
That
really
all
need
changed,
not.
right? I already had the omega answer, but I didn't have R plus, I had 0.
right.
But you can have R+.
Yeah.
Okay. And the relation to the to rescaled convergences, this sort of Henry Cunning and Feijao, is that this thing converges. So if I take something generated like this, I generate the individuals, I generate the connections from this thing I handed you, it is going to converge to the function I used to generate it, the W that you got when you walked into Facebook as a new employee in the rescaled metric. If rho goes to 0, but the average degree diverges. Okay, so this is really corresponding to what's going on in your rescaled metric. Okay, so they're true. They're true to shift mine off too. Usually when it's calling, it's Christian, but calling me by mistake. So
You interrupted the lecture this morning.
may have been. Anyway, so that's one thing, okay? Another totally different approach is something called a Graphon process. So this work, the first time I ever saw it was Caron and Fox in the case of a W, which was a product function, okay? So it was like W of X and Y was like G of X times F of Y. Okay, so
One case, right? So
what?
sometimes
It's a
it's
rank 1 case, exactly.
Actually, F equals G.
Oh, and actually F equal G. That's true because it has to be symmetric. Okay. So, and then Roy and Veitch also did a generalization of this, although we were the ones who studied the notion of convergence when we did it with, and they studied some beautiful extensions called Graphons, which I will talk more about later. And this is work we did with Nina Holden and Henry Cohn. Okay, so I'm going to have a sigma finite measure space and a graphon. Okay, and now what I'm going to do is I'm going to have this Poisson process of points that I generate. Remember, these points are going to be individuals with heights and ages and areas they're interested in, and areas they hate, like some of us are not as big sports fans or whatever. So they're being generated as the points of a Poisson process with intensity T times mu. So mu is the measure that determines what these features are likely to be. No, not too many 7-foot people, things like that, 7 feet people. Okay. And then what I'm going to do, because I've got a W, I'm going to connect them with probability W. Okay, so this is how likely am I to connect with somebody of the same gender or a different gender or this or that or whatever, right? Or, an undetermined gender. And then what I'm going to do is I'm going to remove all, isolated vertices and spit out a finite graph at time t. So let me show you how this works. So I have reduced this very high dimensional space of my height, my weight, my interests, my whatever, to one dimension here. And this point came out first in my Poisson process, and this point came out second, and this point, and this is a one-dimensional, therefore not at all faithful projection of this very big space onto one dimension. So they come out here. And then what did I do? So these came out, and I flipped my W-weighted coins, and I said, okay, X1, try connecting to X2, tails. Try connecting to X3, tails. Try connecting to X4, tails. So X1 didn't get connected. X2, you flipped it, it got connected to X3, it got connected to X4, but when I flipped my 3-4 coin, nothing happened. Okay, my W-weighted 3-4 coin. Okay. What?
Why is the projection important?
The projection is not important. I'm just trying to draw it for you. Okay. Right. Now, at time 2, what has happened? 3 more points have been born. X5, X6, X7. Okay. So X5, oh my, X5, I flipped all the 1s and 2s and whatever, and and nothing attached. But and then X6 landed up attaching to 2 and 4 when I flipped my coins, but nothing else, okay? And then X7 came in, and lo and behold, it attached to X1. So now X1 shows up, okay? Because now all of a sudden, it's not isolated anymore. Okay, so things can appear when someone attaches to them, okay? So this is some weird process, right? And Corona and Fox did this in the case W is f of x, f of y. And so we showed in this paper that the graphon process that you generate, I'm going to get this sequence of graphs. I got a GT1, a GT2, a G, right? Is going to converge to the W that it was generated from in the stretch cut metric, okay? So in other words, this sequence of graphs is faithful in that sense to the W it was generated from, to the coin flips it was generated from that function.
How does the stretching work? I mean, the stretching is when you say convergence, is the stretching somehow happening along the limit, or?
Yeah, so actually, what I could do, and I may talk more about this in the CARP lecture, but really I should be extending this, okay? And what's happening is that I'm recording these points as they come up, okay? As I'm growing this thing, okay? So I'm no longer restricting these points, right? And so this is like a graphon process that's generated. So here I have all my points, x1 through xn, if I'm at, and here I have all my points, and these are appearing when they pair with somebody else, okay? And so this is the process that's generated, and that process converges to that W in the stretched metric.
I think what you're confused about, which is sort of good to be confused about. When I take this sequence of graphs and I just draw these vertices and stretch it, it looks to you probably as if I just thin everything out and things get sort of more and more widely spread, right? But remember, this is this infinite for measure preserving transformations. And once you apply them, you effectively now order the vertices by time. And now if you think in that domain,
Okay.
you sort of have this integral function, and now the things far out will be sparser and sparser. And that's why it converges to a picture.
And then the inhomogeneous random graph will look more like this. I'll focus on the second model and graph X's, which I haven't defined for you in the curve, which were defined by Weinreich. Okay. And so now, how do I estimate? So now I've seen that if I have a graph, a sequence of graphs, I can get a limit under many circumstances, even for sparse graphs of unbounded degree. And if I'm given a symmetric measurable function on a sigma finite measure space, which has features and sigma algebra and a measure on those features, okay, then I can generate representative graphs. Now, given a graph, given like one sample of a graph, I take a snapshot of a graph and I ask you, can you estimate what the corresponding graphon is? Okay, now I am Facebook. I take a snapshot of my graph and I ask you, can you estimate it? I can ask you, can you estimate it quickly? I don't know how to do that, but I will ask you, can I estimate it?
Step graphons.
What?
By step graphons. Step graphons.
Yes, yes. And
That's
then,
why.
well, okay. No, she said step graphon. So yes, so the question is, how would you do this? Okay. And this is work that we did with Shishendra Ganguly in like 2015 or 16, but which finally got published.
That's
So
not our fault, or is it just took forever to get right?
it took forever to get referee. I mean, it was somehow, anyway. So we estimate, what we're going to do is we're going to estimate W by the best K-block approximation to the adjacency matrix, okay? We're going to use a least squares algorithm, and the reason that we do this instead of some of the more conventional ways of doing it is things can explode, actually, if you use some other algorithms. So we're given an input graph with an adjacency matrix A. So this is your snapshot of Facebook or LinkedIn or something. And an integer K, I'm going to ask you to get like a K block approximation to it. And what I'm going to do is I'm going to find the best K block approximation to it. So I'm going to take my thing A, I'm going to look at the matrix B. And whenever I look at a matrix B, I'm going to first go over all permutations of B, okay? Find the minimum one of those. And then I want the B that minimizes, okay? So for every B, I'm going to pick the element of this equivalence class that gives me the lowest one. And then I'm going to say, okay, and now I'm going to find the best B, or the best element of the equivalence class, B. And so this is going to run over, this is just like to make sure that they're.
Nearly equal sizes, right?
What?
The pre-image is nearly equal sizes.
Yes, yes, that's all this is saying, exactly. And I'm going to output the empirical graphon corresponding to this, okay? The W that's in blocks, basically. And as n tends to infinity, this empirical graphon gives the best block model approximation to W in the L2 norm, as long as W is in L2. The density is going to 0, so it's a sparse graph, but the average density is blowing up, okay? And here this D2, it's the L2 norm of the difference between the one and all measure preserving bijections over the other one, okay?
So we should probably mention that this algorithm is not new, was used by several other people. And in the dense case, somebody in the audience is here. Yes.
The sparse case.
No, but you think, well, even in the, so first the dense case, okay,
This way.
first it was in the dense case, people showed that actually the bound you get on that is optimal, min max, and then she proved that for the bounded, so for bounded graphon, that it's min max optimal this algorithm, and then we gave bounds in the unbounded case, but we didn't prove it's min max optimal. I think that's still open.
But you don't need the upper bound from the sub norm?
No, it's just an L2.
And it does get a little hairy in the proof, but I mean, it's what you would hope for, but the proof, it just has to be an
And I'm
outtake,
sure the
that's
bounds
all.
are not optimal.
Oh, they're awful. I mean, just think, I think that they're not optimal,
Well,
yes.
they may just have some wrong numbers, but
Yeah. Yeah, and of course, if you actually try to do this in practice, it's going to take you a bit. Okay. But at least you get, you know that they are estimatable, yes.
So I was wondering in the optimizations that how the matrix size, does the choice of the norm with the measures? Like
Choice of the,
norms, here we choose the 2 norm, or we can choose the other matrix norm, or does that make a difference, or it's
we proved it for the 2 norm. I think, could we do it for other LPs, Christian?
So
I mean-
proofs get hairy for the following reason. If you want to minimize the L2 norm, you differentiate. You get some linear object. Okay. Then you can take expectations of that and you can prove concentrations, Chernoff, and so on. If you take another norm like the 3 norm and you differentiate, it's not linear anymore. You don't know how to calculate the expectations. And I know it. Would you know how to do it in the 3 norm?
Well, at least for in one norm, for bounded graphons, it's quite easy. Just taking equivalence between the 2 and 1 norm. In cut norm, doesn't make sense because the Jesus matrix will be very different.
One and cut norm is also, but any other norms gets it.
So now private network estimation. So this was with me and Christian and Adam Smith. And then Ilias Adi, is he here in the other program or do you know? No. Anyway, he did a real strengthening with us a few years later, which I'll mention. So, even for a database, there's privacy issues. And of course, Dwork and Adam Smith and others developed this notion of differential privacy, because even for a database, if I take Bill Gates in or out of a database that has to do something with income, you're going to notice it. Okay. Privacy problem for graphs is even worse because connections reveal information about people. For example, in 2009, Jerrigan and Mystery showed that, with high probability, they could estimate someone's sexual orientation from their links on Facebook. Okay, it's by virtue of your connections, and if some of your connections say something about themselves, and so anyway, so we need to do something about this. And so there's a notion of differential privacy called no differential privacy. So we say that a given algorithm A is epsilon no differentially private if for all graphs, G and G prime, all graphs that differ in at most 1 node. So that's the graph with or without Bill Gates in it, okay, or with or without me in it is what I care about. And all events in the output space, so that algorithm might give anything on the 2 graphs, putting me in or not in is only going to make a 1 + O epsilon difference in the output, okay? So you can't learn very much about me Okay, you can't learn very much about my income or my sexual orientation or whatever. From that. So it's a well, people had worked on edge privacy before, which is a much easier notion. Okay, that says if you remove an edge or you keep an edge in, what happens? But that's not really what I'm worried about because I'm not an edge, I'm a node. Okay, and so I don't care if you put my, my edge to Christian in or out. What's going to happen? It's, how about all the other ones, right? How about?
There might be situations where you really may not want people to know that you actually have some context, some rich context.
True, but it's the notion of can I be in this network and people not be able to know things about me is really the node notion. So people have worked on edge privacy and dense graphs and stuff. So we used this idea in the proof called the exponential mechanism. So what you want to do is if this is the output, what I want to do is I want to be generating some B's that are close to this. In what sense close? Well, again, when I generated B, I have to go over the whole possible equivalence class of that one B. And then I want to generate exponentially in how far I am from that. Okay. And what we proved is, so here we are at bounded, it's much less than the other things we talked about. If W is bounded, if the corresponding W, which has generated these networks, is bounded, if the density is going to 0, and here, rho not only, this should be N rho N.
No, it's okay.
No, because it's right, because rho N, because I put the 1 over N there. I shouldn't have, but right. So if M rho N is going to infinity at least as fast as log N, so not just going to infinity, but at least as fast as log N. So in the first piece of work, we got upper bounds. And in the second piece, and not very good lower bounds, okay? No lower bounds. And in the, and then what we got with Ilias was that the upper bounds matched the min-max lower bounds in the limit of no privacy. Okay, so we have not deteriorated the estimates as we go to no privacy, okay? You might think that as we made estimates, we were doing so badly that in the limit of no privacy, we would be getting something worse, but we don't. Okay.
So again, for sort of historical concept, our paper with the first one, was independent in parallel with your paper, but we didn't do maximum lower bounds, and our upper bound was off by a square root from your upper bound, but we did differential privacy. And then in the paper with Ilias, we improved our bound so it would match our bound in the limit of no privacy, and we showed how the privacy going to infinity, how it's
0.
That it's this.
Oh, going to infinity. Okay, yes, privacy. I mean,
Right, okay.
yeah, whatever.
Right.
I didn't know.
No privacy.
Okay. No privacy. Right. So, the question was, how badly have we missed in the case of differential privacy from the optimal stuff that you had gotten? And with Ilias, we redid it so that doing it differentially privacy with differential privacy
it was
deteriorate.
before not even known for GNP. So for people for GNP, the upper and lower bounds of how private you can do it were off by a factor of square root of 2. So nobody knew how to, and so we were really astonished that you didn't know it. People didn't know it.
So the upper bound in the case of privacy depends on epsilon, right?
Yes.
Yeah.
Do the optimal dependency on epsilon in the
For
lower bound?
G and P, we have optimal dependency up to some logs. So for G and P, your naive algorithm, you would just say, well, I independent, so I estimate the edge density. And that is edge private. And now you add sort of edge noise to it. That is actually the optimal edge private algorithm. But it gives you a so this is interestingly not the best algorithm if you want node privacy. So you have to be much more clever how you add noise into your system if you want node privacy. And that if you do it right, you get sort of better by a square, almost up to a log.
And that's what Ilias really helped us to do. Okay. So he's great. He's your student, right?
Former, unfortunately.
Former student. Yes, he was your student. That was during an internship that he had with us, but we were really surprised that it was possible to improve it that much. Okay. So now we've done this. And now, I guess I have a few minutes for an application. Okay.
Here's the boss, he can give you 2 hours.
12 minutes at least.
Okay, good. So recommendation algorithm. So, kind of movies and people, for Netflix or Hulu or Amazon, products and people, whatever. And I'm trying to estimate how much a certain person is going to like a certain product or certain. Okay, or network completion. So I know that a lot of economists, developmental economists, they measure some network, but from that they want to estimate maybe how you complete that network, right? What other connections are likely to be there or not be there based on sparse measurements. Or network completion when you have different kinds of things like, okay, you don't only have whether they're connected or not, but how much they like each other, or how much email they send, or how much they have commerce with each other, they sell things to each other, whatever. Okay, so this is really a matrix completion problem. We have people and we have movies and we have ratings between 1 and 5, but only very, very sparsely. Okay. And so how are we going to estimate that in the same entry that I want to know whether I'm or you am going to like, some crazy movie that's out now. Okay, so Aldous Hoover, you learned about it yesterday. So for this, even though this graph is sparse, all we have to do is we have to do like dense Aldous Hoover for this. Okay, so you probably learned from Christian, I don't know, did you get to the Monday, that Aldous Hoover is kind of a cool generalization of Differential's theorem to 2 dimensions, right? And so, whereas Differential's theorem, pull your urn and stuff, oh, it's so surprising, I can predict. If I condition on the density, I can predict all these things that I thought were dependent on each other. So what Aldous Hoover says, basically, I like to view it this way if I view it as kind of a latent variable model, okay, is that exchangeability and ergodicity lead to a latent variable model. So exchangeability, the individuals we're talking about, can be changed, okay? And ergodic, if we don't have ergodicity, we at least have to send 1 ergodic component. So what Aldous Hoover says, reinterpreted in the light of using the results of Graphons for dense graphs, is that if you have an infinite dense array of dependent random variables, okay, which are exchangeable and ergodic, then there is a feature space, okay? There is a set of attributes, for example, such that if you condition on the ergodic component and on the features of all the vertices, the entries of the array are actually independent of each other. And the distribution of those entries depends only on the features. Okay, so that's kind of like the machine learning view of,
Can I
yeah.
just interpret in terms of the metrics, whatever metrics is, metrics are decomposed into irreducible components. It is what you call.
No, these are
No?
different.
What is algorithm component then? We
You
didn't,
have
it's not
you have a
irreducible and
probability, you have an infinite random matrix.
You're
And
right.
that's-
And they're being
If
generated
you
by.
look at the all probability distribution, and you take some corners and
Corners,
or if you want, you look at the things which have a trivial sigma algebra with respect to your metric of, I don't know, whatever, on your probability spaces on infinite
I also
random
forgot that there
matrices.
is a probability space dangling on. I'm living still in a finite space, that's why. Yeah.
No, this
Anyway,
doesn't work.
So,
There's no
I see.
exchangeability theorem for finite spaces. You need an infinite random matrix. Okay. And if in this random matrix setting, if you look at blocks which physically don't overlap,
Yeah.
if their distribution is independent, then this thing is ergodic. Okay, forget that there's a word ergodic which means something.
I find
So if that is independent, then you can model it.
Within each one,
non-random.
even though these entries are dependent,
but within
if I fix on the right component, then I write on one component, then they're effectively independent of each other. I mean, that's a way of interpreting Aldous Hoover, which I think is really, really cool, actually. And then the distribution of them depends only on the features. So what this corollary says is that our matrix, which is the matrix of individuals and the matrix and movies, only depends on the features. And then these are independent random variables, which we can take to be random at 0, 1, like depends only on the movies and the people, even though a priori you would think these are dependent on each other, but only through those variables. So what this tells us is that this y can be written as a function of the people and the movies and some random thing, which I'm going to say to be okay, I'm going to sample this with probability p. I'm going to sample you and the movie with some probability p, which is small because I don't want to look at all people in the world and all movies. Okay, so this is basically telling us we can represent it by a W. Okay. And then let D be the dimension of the latent space or the max dimension of the two spaces. Okay, the space of all movies and yeah.
Is the probability P the same for all entries?
What I'm going to do is I'm going to sample this. So I give you the output of it. Netflix has sampled with some probability P, which is very small. In the people putting in their votes, let's say, is the same as sampling with probability P.
Yeah.
So imagine that there exists this infinite matrix of rating. Every pair of movies and users have rated each other, but I only observe.
I serve a snapshot.
And that's a P.
Yeah, but the sample matrix is the pattern of the sampling is uniform. It's not doesn't
Right, but
Right.
it could
doesn't
also,
cover like
okay, so it
tail.
could depend on the feature, as long as P is, if you scale it by something, and once you scale it, it's upper bounded. Then it would, so if it's.
So we're going to see how
It could
the P depends on N.
Well, yes, in your thing, in our thing, it can depend on N. But it could, in addition, be multiplied by a function which lies in 0, 1. It does depend on the features and it wouldn't change X. Because you just were arguing whether I watch a movie or not will depend on the answer.
So, given this observed data matrix, Y, can we learn the expectation of Y And I mean, this is stupid, but you know, I could do this separately for ratings 1, ratings 2, ratings 3, and it's kind of trivial. And ideally, we would like to estimate this for P goes like 1 over N, right? I want to know how to do this if I haven't rated, you know, if I've rated on average, you know, not too many of the movies, right? So Chatterjee, his previous results required P to go like N to the -2 over D over 2, which was not very useful for large N and large D. I mean, it was great that he got some bound, but one wanted to improve that bound if you want to, if you want to apply it to real situations where you can't be rating that much, okay? Or sampling that much if you're trying to do a network completion problem or whatever. Okay, so the challenge of sparsity. Challenge of sparsity is that, you know, there could be no overlap. You know, I want to use Shavik to, you know, help learn about what movies I might like, but oh my God, we've had no overlap in the movies that we've watched. Okay, so what am I going to do? And Abe Sandin did this, something like this. So let's go on. Let's look at expanding neighborhoods. So I rated these 2 movies. These 2 movies are also rated by some other people. Those people have rated some movies, and lo and behold, I finally get some overlap. Okay. So how far out do I have to go in these expanding neighborhoods to have a reasonable chance of an overlap? It's the birthday paradox, basically, right? How big is my class until I'm going to have someone else with the same birthday, right? And so the birthday paradox says that you want the boundary to be greater than square root of N. So how far out do I have to go to get a boundary of that size? The radius has to be like log N over log Pn, where P is the sampling density, because I have to have sampled it. Okay. And then what I'm going to do is I'm going to compare the product of the ratings along the path. Okay. And I do that basically with my Graphons. And so this is work with Christina. She was Christina Lee. She's now Christina Yu, and Deborah Vratshaw. And so assuming W is Lipschitz and rank D.
Christina gave a talk in the first, not an hour tutorial, but it's lesson.
Okay. And this is observed with some probability that now does go like 1 over N, although it has this nasty D squared in front of it, but it's still going like 1 over N. Then the mean square error goes to 0 pretty quickly. Okay. And, you know, and if P is of this order, so if we give it some logs, then with high probability, this is going to happen. So it's much better than the previous result, which was great at the time, which could only handle this, allows for general noise and that kind of thing, which you're going to find if you're trying to estimate Graphons. Okay, so dense graphs, metric. So, okay. So Christian told you about all these notions of convergence. For sparse unbounded degree graphs, we need new notions of integrability, like uniform upper regular sparse graphs, to make sure those things don't go off to infinity, uniform tail regularity, and make sure that mass isn't leaking out. And the second notion can be extended to give compactness and subsequential convergence without the assumption of uniform tail regularity if you complete this basic Graphons, which I'll do in the CARP lecture. Then we have these non-parametric models, these inhomogeneous random graphs, and the Graphon processes, very different, two nice ways of doing it. We can consistently estimate very general unbounded sparse degree power law graphs corresponding to an unbounded W. As far as W has to be an L2, And we can consistently and differentially, privately estimate these for a bounded W, with our results reducing to your results as the privacy goes to your min-max lower bound, okay? And under the assumption of an underlying latent Graphon model, we can design new improved matrix algorithms. Yeah.
Thank you so much. Any comments, questions?
Question on matrix completion. So what is how the algorithm is working?
How is what working?
The algorithm, what is the idea? What is
Which?
How's
the
the algorithm?
matrix completion? What is the exact algorithm?
So the effective algorithm is just you look at this very sparse matrix.
Oh, you're asking for the differential privacy.
No,
Matrix completion.
it's a matrix completion.
Oh, the matrix.
So the algorithm, so you have this sparse matrix, and you essentially take it to higher and higher powers until actually, so if you think it into the graph, I have a sparse matrix, I essentially go out sort of this effectively a branching process of slightly divergent degrees. And then I take the transpose of the matrix, and then the
You want
matrix.
us to do it like an operator, like you would expand an operator?
Multiply matrices.
Yes,
Mhm.
and multiply matrices until the resulting matrix is dense. And now I consider, so now I have a feature, so let's say I have on one side the users, I take the matrix to the, so I do A transpose, and so on. And then the feature of the user I is the vector of entries you see after having multiplied the matrix often enough, which will be dense. So therefore, if I now look at my feature and your features, they start to have overlap in this vector space. And I call them similar if they are near in that space of vectors.
So does the time of convergence, do you have an idea about the time of convergence?
Of course, she wanted, you want to go back to the theorem? So this is about the error. Oh, you want to know how long it takes?
Yeah.
Well, you went out log n over log
But
n.
it's sparse, so I have no idea how.
Because I'm not sure, but since the is about the like suboptimal compared to the standard matrix function.
So we,
Maybe.
Seems
Yeah, it could
not
be
generally it's not because it's suboptimal, it's not what in practice either, but like a standard internal optimization.
so that actually gives you bounds which are
It's
again.
optimal. It's not to be optimal. This one looks a little bit.
So this can't be so it's optimal just in general, or do you need some assumption on sort of the rank of your, I mean.
It's assumption of sampling scheme, but we are in the form sampling scheme, so it works for if it was for more general sampling schemes. But we can discuss it all.
But don't you need the density of observation to be somewhat large? Typically, which
It should be at least from the rank times the larger dimension, or exactly the same assumption. Exactly the same assumption. Anyway, if you don't have it, you cannot do it. It is a little much lower.
We should discuss that.
But
Yeah.
we're-
We should discuss that. Okay.
But you said this works for any matrix.
Yes.
Or does the matrix have to be actually, do we know that the items?
It should be low rank, right? It should be rank most.
Right. Oh, but here the matrix is not rank, right? So it's only the generator.
Yeah.
So, but this matrix might not be low rank.
But the matrix what you observe is low rank.
No, we don't know.
W is the W's that we're multiplying out or not.
Right? You have a
Low
dense, you have an you take an underlying dense matrix and you
Should be rank.
sparsify it. So you take a graphon, you generate an underlying, you take defined by graphon, rank D graphon,
Yeah, it should be rank D, right?
right? Then you generate a matrix that's not rank D anymore.
Sure, but I'm thinking about the original matrix. It should be
The original matrix is rank D, but the matrix of probabilities, oh, that's still rank D. Right?
depends if you conclude with what you complete your matrix, right?
Yes.
Absolutely. That,
And then you put error on top of it. So it's rank D plus perturbation.
it may work also as a result of one right about it.
Okay, we should discuss what we really interested. So you think there might be just some results that just false for general matrix if you just
Of
have
rank
the
of given right.
and for perturbation of, because this matrix is not quite rank D for perturbation.
But that's not, I mean, that could be controllable.
Right. So maybe there's some general algorithm which goes fast.
Well, nuclear minimization goes fast for reasonable size of matrices, but then you get the matrix factorization algorithms, which converges reasonably well to larger matrices. But probably it's better to discuss.
Yeah, and let everybody go to Labor Day begin.
I have a question about this last part too, whether the algorithm is equivalent to making a bunch of random walks. Basically, by multiplying the matrix with the matrix.
Oh, backtrack. Maybe
These
backtrack.
backtracking random walks that people like Lenka and Elkanon and others have looked at.
Is that equivalent conceptually to doing that, or?
So, okay, so I don't know whether in this setting, but if instead, so here we have a rank D object, right? You could instead have a D by D stochastic block model which generates that. And then for that we know, so this algorithm was actually developed by Abe and Sandin for that case. We also know that belief propagation works. We know that spectral works if you cut off the large degrees. And we know that the non-backtracking matrix works too. And so maybe they all will work here as well. With both parts. It's not equivalent, they're all different algorithms.
Yeah,
But
I was wondering if it works because of that.
We didn't consider it actually.
Let's see any more comments, questions. Let's mention it again. Anniversary.
We didn't know it was our anniversary. I woke up this morning to my aunt having texted us. I always forget. Just